Welcome back to AI Academy's course on Python for data science. So, after exploring our data thoroughly, understanding each variable's distribution, and how they interact with each other, we're now confident to take a significant step forward. In this lecture we will be building a logistic regression model. This type of model is a primary in the machine learning toolkit, particularly effective for binary classification tasks, such as predicting whether individuals earn more or less than $50,000. So, why logistic regression? As logistic regression excels at binary classification because it doesn't just predict categories, it calculates probabilities. For our income classification, it means not just determining if someone earns above or below $50,000, but also how likely that prediction is to be accurate. So, our first step would be to prepare our data for the model. Before we can feed our data into a logistic regression model, there's a crucial preprocessing step we need to tackle: converting categorical data to a numeric format. Most machine learning algorithms, including logistic regression, require numerical input to function correctly. So let us move to the integer encoding of categorical data because our target variable, salary status, is categorical with the labels less than or equal to $50,000 and greater than $50,000. To make this suitable for our model, we'll convert these labels into numbers. Here's how we do it. Less than or equal to $50,000 will be mapped to 0. And greater than $50,000 will be mapped to 1. After executing this code, salary status in our data frame will now reflect as zeros and ones, which are much more understandable for the logistic regression algorithm. Please note that the salary status variable has extra leading space for the categories, and we have handled the same in salary mapping dictionary by including them in both the condition, as you can see. Now that our data is appropriately encoded, we are set to dive into the logistic regression modeling. However, before we proceed with building and training the model, it's critical to ensure everyone is on board with the changes we've made to our dataset and understands why these steps are essential. Let us now move on to looking into the process of using one-hot encoding to handle categorical variables in data preparation for machine learning models. We will look into the transforming categorical data with one-hot encoding. As we continue preparing our dataset for logistic regression, it's crucial to address how we handle categorical variables. While integer encoding is straightforward for binary categories, as many variables have multiple categories, which requires a different approach. So, one-hot encoding is a method to convert categorical variables into a form that could be provided to machine learning algorithms to do a better job in prediction. It creates additional columns for each category of the variable, each representing a binary presence of the category. For implementing one-hot encoding, Pandas offers a straightforward way to implement one-hot encoding via the getDummies function. This function transforms each categorical variable into multiple binary columns, one for each category. After applying getDummies function to our data, let's look at what happens to categorical variable like job type, which had several categories. So, originally, job type included categories such as private, government, self-employed, etc. And after one-hot encoding, these categories are split into separate columns like job type private, government, self-employed, etc., with each row marked as 0 or 1. For example, 1 under job type private indicates the individual's job type is private. And 0 would indicate the individual is not in a private job. This method allows our model to understand the data without any implicit ordering. By converting each category into a new column, the model can more easily leverage this structure to make better predictions. So, one-hot encoding is particularly useful when dealing with categorical data with more than 2 categories. It expands the data's dimensionality but provides a clear, interpretable format for building robust machine learning models. This approach ensures each category is unique. Let us now move on to preparing data for machine learning. As we progress with our logistic regression model, our next step is to ensure that all data, specifically our categorical variables, are properly encoded and ready for use with machine learning algorithms. And we can see that we've successfully converted all categorical string values into integers, and now we'll organize our data into n variables. To do the same, we would need to structure our data so, in machine learning, we often refer to the variables we predict as the dependent variable, denoted as y, and the variables we use for making predictions as independent variables, denoted as x. For doing the same, we will store the list of columns to a new data frame called column list. So, with this we can see that the column list data frame has only the names from the data frame. Now we need to separate the input variable from the data, for we will exclude the salary status from the data and will call it as features. So now we can see that the features data frame does not have the salary status as a part of data frame. Now that we've identified which columns belong to features and which column is our target, we can extract these into separate variables. This separation allows us to handle them appropriately during the modeling process. X contains the data from our features, effectively all columns except salary status. And Y captures the salary status values, which we'll predict using our model. Let's take a moment to understand the structure of our data. X has dimensions of 30,162 rows and 94 features, reflecting the number of independent variables we have. And Y is a vector with 30,162 entries corresponding to each row's salary status. By carefully preparing and verifying our data, we ensure that our machine learning model has a solid foundation. This step is crucial as it directly impacts the model's ability to learn and make accurate predictions. We've successfully set up our independent variables x and our dependent variable y, and we're now ready to proceed to the actual modeling. Next, we are going to split the data into train and test. We have to divide the data set into a training set and a test set. Let's reframe this section of your lecture where you introduce the train-test split process in preparing your dataset for modeling. The goal is to ensure your audience understands the necessity of this step and how it's executed. Having prepared our data with the necessary feature selections and encodings, we now turn our attention to one of the most critical stages in machine learning by splitting our data into training and testing sets. This step is crucial for building robust models that not only learn well but also perform well on unseen data. So, why to split data? In machine learning, we build models on known data called as training set and test them on unseen data known as test set to evaluate their performance. This approach helps ensure that our model can generalize well, not just memorize the data it has seen during training. For implementing train-test split, we'll use scikit-learn's train-test-split function to divide our data. This function shuffles the dataset and splits it into train and test subsets according to the ratio specified. First, we import train-test-split module from scikit-learn. Then we split the dataset into train and test set, and we give test size to 0.3, meaning 30% of the data is allocated to the test set and remaining 70% is used for training. And we also set random state to 0. This parameter acts like a seed for the random number generator used in splitting the dataset. Using the same seed ensures that the split is reproducible, meaning you get the same training and testing data each time you run your code. If we observe our split, X-train contains 21,113 observations across 144 features. Y-train contains the corresponding salary statuses for these observations. X-test contains 9,049 observations across the same 144 features. Y-test contains the corresponding salary statuses for these testing observations. With our data now divided into a training set and a testing set, we can proceed to build and validate our logistic regression model. This setup not only helps in tuning our model but also assures us that it can perform well on data it has never seen before. Let us now move on to building and testing our logistic regression model. First, we create an instance of the logistic regression classifier. By importing logistic regression from sklearn linear model, we create an instance of the logistic regression classifier. Once our classifier is initialized, we'll fit it to our training data. This process involves training the model to understand the relationship between our features and the target variable. By fitting the model, it learns from the input variables x_train and the output variable y_train. After the model is trained, we can examine its coefficients, which represent the influence of each feature on the prediction. Coefficients tell us the weight or importance of each feature in predicting the salary status. So, the positive coefficients indicates that an increase in the corresponding feature increases the log odds of the dependent variable being in the positive class, like salary greater than $50,000. For example, if the coefficient for a feature is 0.25, it means that for every unit increase in that feature, the log odds of the salary being greater than $50,000 increases by 0.25. And a negative coefficient indicates that an increase in the corresponding feature decreases the log odds of the dependent variable being in the positive class. For example, if the coefficient for a feature is -0.5, it means that for every unit increase in that feature, the log odds of the salary being greater than $50,000 decreases by 0.5. And the magnitude of the coefficient indicates the strength of the association between the feature and the dependent variable. Larger magnitudes, positive or negative, indicate stronger relationships. If we have a feature age with a coefficient of approximately 0.025, this means that for each additional year of age, the log odds of having a salary greater than $50,000 increases by 0.025. Another feature with a coefficient of approximately -1.17, this means that for each unit increase in that feature, the log odds of having a salary greater than $50,000 decreases by 1.17. Intercept is the point where the decision boundary intersects the axis. In a logistic regression model, the intercept, also known as the bias term, is a key component of the logistic regression equation. The logistic regression model predicts the probability of the default class, usually class 0, based on the linear combination of the input variables. The intercept value is approximately -2.083. This means that when all the input features are 0, the log odds of the default class, class 0, is -2.083. Now, let's use our model to make predictions on the test set, which the model has not seen during training, to evaluate how well it performs. These predictions will tell us whether individuals in the test set are likely to earn less than or equal to $50,000 or more. And the print output will be in the form of 0 and 1. After training our logistic regression model, the next crucial step is evaluating its performance. We'll do this using a confusion matrix and calculate the model's accuracy. A confusion matrix is a simple yet powerful tool for summarizing the performance of a classification model. It helps us understand not just the errors of the model but also the types of errors that are occurring. A confusion matrix is a table used to evaluate the performance of a classification model. It provides a summary of the prediction results on a classification problem. The matrix shows the number of correct and incorrect predictions broken down by each class. In a binary classification problem, the confusion matrix has 4 components. True positives, the number of positive instances correctly predicted as positive. True negatives, the number of negative instances correctly predicted as negative. False positives, the number of negative instances incorrectly predicted as positive. False negatives, the number of positive instances incorrectly predicted as negative. Given the output matrix, the first row corresponds to the actual negative class, class 0. True negatives is 6,322. This means that 6,322 instances of the actual negative class were correctly predicted as negative. And false positives is 501. This means that 501 instances of the actual negative class were incorrectly predicted as positive. The second row corresponds to the actual positive class. False negatives is 920. This means that 920 instances of the actual positive class were incorrectly predicted as negative. And true positives is 1306. This means that 1306 instances of the actual positive class were correctly predicted as positive. Let us now move on to calculating the model's accuracy. So this method measures the proportion of total correct predictions, including both true positives and true negatives, among the total number of cases examined. The output tells us the percentage of the test set that the model predicted correctly. In our case, if the accuracy is 84.3%, it means our model correctly predicts the salary status for 84.3% of the individuals in the test set. While accuracy is helpful, understanding misclassifications can provide insights into how the model might be improved. Misclassified samples are those instances where the predicted label does not match the actual label. So, why test predictions not equal to predictions compares the actual labels with the predicted labels. The result is a Boolean array where each element is true if the corresponding prediction is incorrect or the predicted label does not match the actual label, and false if it is correct. The output misclassified samples, 1421, indicates that out of the total test samples, 1421 samples were misclassified by the model. This means that the model's prediction did not match the actual label for 1421 instances. By analyzing the confusion matrix and accuracy, we gain a comprehensive understanding of our model's performance. These metrics help us not only to validate the effectiveness of our model but also to identify areas for improvement. Understanding where the model fails to perform can guide us in refining our approach, potentially by tuning hyperparameters or reconsidering feature selection. Okay, let us now move on to enhancing our logistic regression model. So in our initial analysis in last lecture we have identified that certain variables showed limited influence on the outcome. These are what we call insignificant variables. Removing these can sometimes improve model performance by reducing complexity and focusing on more impactful data. By simplifying our model in this way, we aim to make it not only faster but potentially more accurate by avoiding overfitting to noise in the data. So, let us start rebuilding the model. With the revised dataset, minus the insignificant variables, we proceed as before by encoding categorical variables into dummy/indicator variables, separating our features-independent variables from our target-dependent variable, and splitting our data into training and testing sets. So first we convert the categorical variables into dummy variables. Then we move on to separating input and output variables and split the data into training and testing sets as we did earlier in this lecture. Now, with our data prepped, we create a new instance of the logistic regression model, fit it to our training data, and then use it to make predictions on our testing data. So let's now make predictions on the test data. Finally, we evaluate this new model using the same metrics as before, including the confusion matrix and accuracy score, to see if our adjustments have indeed improved the model's performance. By refining our approach and focusing only on the most relevant variables, we strive to build a more efficient and effective model. This process of iterative improvement is at the heart of data science, allowing us to continually refine our predictions and insights. After simplifying our logistic regression model by removing variables deemed insignificant, our next step is to evaluate whether this streamlining has effectively enhanced the model's performance. Once we've made predictions using our refined model, we'll assess its accuracy. Let's now compare the accuracy of both models and understand the difference. So, the initial model accuracy was 84.3% and the refined model accuracy is 84.21%. The difference in accuracy between the two models is approximate 0.0807%. So, the initial model includes all the variables initially considered for the logistic regression. It did not remove any variables deemed insignificant. Whereas the refined model excludes some variables identified as insignificant like gender, native country, and race. This step is taken to potentially improve the model's performance by removing noise or irrelevant features, thus simplifying the model. The removal of insignificant variables might lead to a slight decrease in the model's accuracy. This happens because, while those variables might be insignificant in general, they could still carry some minor predictive power. Removing them slightly reduces the model's ability to capture those nuances. Simplifying the model by removing insignificant variables can lead to a more interpretable model. However, in this case, the small decrease in accuracy indicates that the removed variables did contribute, albeit marginally, to the model's predictive power. The initial model might be slightly overfitting the training data because it considers all variables, including those with minor contributions. The refined model aims to prevent overfitting by focusing on more significant variables, which can sometimes result in a minor accuracy trade-off. The accuracy of the refined model is very close to the initial model. The small decrease, 0.0807%, indicates that the removed variables had a minor impact on the model's predictive power. The refined model, however, might be more generalizable and easier to interpret, which can be beneficial for understanding and maintaining the model in practice. The decision to use the initial or refined model depends on the specific use case. If interpretability and simplicity are more important, the refined model might be preferred. If achieving the highest possible accuracy is the priority, even a minor improvement, the initial model could be the better choice. If the goal is to streamline data collection and maintain a simpler model for operational efficiency, retaining the refined model could be beneficial, especially when the loss in accuracy is minimal and acceptable given the context. Deciding whether to use the simplified model involves weighing the benefits of a less complex model against the slight decrease in accuracy. This decision should align with the specific needs and constraints of the project, such as the ease of data collection and the criticality of predictive precision. Okay, we'll now shift our focus to the k-nearest neighbors, KNN, model, another popular choice for classification tasks. This approach will help us understand how it compares to the logistic regression model we've previously discussed. So, the k-nearest neighbors, or KNN, is a simple and intuitive machine learning algorithm used for classification and regression tasks. It makes predictions based on the idea that similar things exist in close proximity to each other. To implement the KNN classifier, we first need to import the necessary library from scikit-learn. Let us now configure and train the KNN model. With our libraries ready, we'll create an instance of the KNN classifier. We'll set n neighbors to 5, meaning the model will consider the 5 nearest neighbors to determine the class of a new sample based on majority voting. Then we fit the model with training data. After training, it's time to use our KNN model to make predictions on the test data. This step is crucial to evaluate how our model performs on unseen data. To better understand the classification results, let's visualize the predictions. This can provide insight into the model's performance and any potential areas of improvement. So, in the plot, x-axis represents the feature x-test0, which is the first feature of the test data. And the y-axis represents the feature x-test1, which is the second feature of the test data. And each point represents a test sample. Color indicates the predicted class of each sample, like red, one class, like greater than 50,000. Blue, another class, like less than or equal to 50,000 foot. Transparency set to 0.6 to allow overlapping points to be seen. Red clusters, areas where the majority of points are red, indicate regions where the KNN model strongly predicts the greater than 50,000 class. Blue clusters, areas where the majority of points are blue, indicate regions where the KNN model strongly predicts the less than or equal to 50,000 class. Outliers, any red points in predominantly blue areas, or vice versa, could be misclassifications or outliers. The effectiveness of the KNN classifier can be visually inspected by how well separated the colors are. A good classifier will have distinct regions of red and blue. With the KNN model set up and predictions made, we've introduced another robust method for classifying salary statuses. By comparing the results of this model with those from the logistic regression, we can better understand the strengths and weaknesses of each approach in handling our specific dataset. Now that our k-nearest neighbors, KNN, model is in place, it's crucial to understand its performance. We'll do this using a confusion matrix, a fundamental tool in machine learning for visualizing the accuracy of a classifier. To optimize our KNN model, we'll explore different k-values, from 1 to 20, to find the most efficient one in terms of reducing misclassifications. We use a loop to run the model for each k-value and record the error rates. After running the loop, we determine that k equals 17 offers the fewest misclassifications, suggesting it as the optimal choice for our data. Through this exercise, we've seen how adjusting the k-value in our KNN model affects performance. With a slight adjustment from k equals 5 to k equals 17, we reduce errors and potentially increase model robustness. Both logistic regression and KNN models show promising results, but fine-tuning and perhaps simplifying the model by dropping insignificant variables could further enhance performance. So, if we compare the accuracy, summary of accuracy comparison. Initial logistic regression model, 84.3%. Refined logistic regression model, 84.2193%. KNN model with equals 17, 84.7828%. The KNN model with equals 17 has the highest accuracy, followed by the initial logistic regression model, and then the refined logistic regression model. The differences in accuracy are relatively small, but the KNN model performs best on this test dataset. This could be due to the way KNN leverages the similarity of nearby data points to make predictions, which might be more effective for this particular problem compared to logistic regression. With this we conclude this lecture and the classification case study focused on predicting individual salary status using logistic regression and KNN models. We've explored model construction, evaluation, and optimization, providing a strong foundation in handling categorical outcomes in predictive analytics. In our next lecture, we will shift our focus from classification to regression. We'll embark on a new case study aimed at predicting the price of pre-owned cars. This regression model will help us understand how various features of a car, such as make, model, age, mileage, and condition, influence its market value. We hope that you have found this course informative and interesting. Please hit the like button and subscribe to our channel and stay tuned for upcoming courses. Your support means a lot and motivates us to create more educational resources for you. Stay tuned for the next lecture, where we'll continue our journey through our course Python for Data Science. Thank you for watching and see you again in our next lecture.